just have short lessons and go over the key points that are important in each booklet for the exam, particularly the merit and excellence level exams, excellence level criteria. So in your 304.1, the two key things you really look at are electron configurations. Now, electron configurations is pretty much an achieved level, perhaps a merit level, but really achieved. Does anybody have a problem with electron configurations? Or you may not even have started this booklet, so just say, haven't done it yet, so don't know. The periodic trends, you will get a question on, absolutely guaranteed. And this is one of the questions where they look at whether you can get achieved merit or excellence. So just simply knowing the trends isn't enough. So for instance, in your booklet you've got this image and you can see the atomic radius is increasing down a group and it's decreasing across a period, or if you like, it's going the other way, it's increasing going from right to left. Ionization energy goes up, electronegativity goes up, it increases up a group, not down a group, and your electronegativity and ionization also increases from left to right across the period. So you do need to know those trends, but just simply knowing them isn't enough. You must be able to explain. And this is why I thought I'd bring in Coulomb's law, because it helps explain why this is happening. So, now, you don't have to know Coulomb's law, but what we're just really looking at is this force of attraction depends on the two charged species, so proton and proton, or proton and electron, or electron and electron. If it's proton and electron, it's an attractive force. If it's an electron with an electron, it's a repulsive force. And it's inversely proportional to the distance. So what I've got here, and you can just Google, say, Wananta coulombs, and you should be able to come up with this simulation, and I think it should be an OTTL. Ha, you were just using it in physics. There's a lot of overlap between chemistry and physics, so it's great if you do both. What I'm trying to show here, I'm just going to clear this, and it's a great little, so I've made it go to 1. Can you see, these are my 2-point charges, so I've only got a positive charge and a negative charge, so we're just looking at an attractive force. And you can see the distance. If the distance is far away, there's not much attraction, it's 0. As I get closer, there's still not much. I get closer, it's still not much, still not much. Okay, but as I get closer and closer, can you see the attraction is increasing? So in your explanation of periodic trends, you need to talk about distance, because you can see that the closer they are, the more they attract. Then I can change this, and I can change the size of the charge. So remember, this is our Q1 and Q2, and if I bring them closer now, if you look at these dots, can you see it's starting to already get above 0? Okay, and you can see it's a lot more, and if I try, say, a much bigger charge difference, other way around, you can see it gets a lot bigger attraction. Sorry, I'm just trying to do too fast, so it looks like a lot of dots. But do you get that idea? That the bigger the charge, the bigger the attractive force. The further away they are, the smaller the attractive force. Good. And that is what you want to talk about in your explanations. So going back to here, what we really want there is that when we're comparing distance, here it's charge, so the bigger the charge, the bigger the force, okay? And the other one is the further the distance, the smaller the attraction. Okay, so you have, as I say, the 3 or 4 periodic trends you have to discuss. The atomic radius, and associated with that is ionic radius, that's why I say it's 3 or 4, and then electronegativity and ionization energy. So, atomic radius, does anybody understand what I've got up there? I mean, does anybody not understand what's up there? We basically work out an average atomic radius by, you can measure when atoms bond, and we say, okay, if atoms bond, especially if they bond with themselves, it's about half the distance. So that's why you'll find if you Google up atomic radius of in one site, and then you Google it up in Wikipedia and then somewhere else, they could all be slightly different. It really depends on, you know, what averages they've used to work it out. But the trend is the important thing. So basically they say, if I say have an iodine molecule, then we can work out the distance. You work it out through X-ray crystallography, things like that, and then half the distance will be then the atomic radius. That's just background. You don't have to know it. Now, I've got a little rhyme to help you remember all the things you need to discuss. So I always think of, you're talking about trends, so think of pens, okay? So P for protons, E for electrons, energy levels, effective nuclear charge. So there's lots of E's there. N for nuclear charge. So that'll be how many protons on the nucleus? That's the nuclear charge. So if you're thinking of your Q1, your Q2, your nuclear charge will be Q1. Then the distance from the nucleus, think of Coulomb's law, that distance. And then shielding. Shielding affects the nuclear charge to make it the effective nuclear charge. So I'll go over those now. But as I say, if you just think of pens as a mnemonic and you think, have I discussed all of those 3 things? So, okay, here, so pretty much it's the distance between the nucleus, so that's why we've got the nuclear charge, and the valence electron for ionization energy and for electronegative, sorry, not atomic radius. We talk about bonding electrons for electronegativity, and I'll talk about it later. So it's nucleus and valence electron, and we're looking at that force of attraction between them. Okay, so here I've got a sort of an image showing the change in the atomic radius, and you should see one thing straight away as you go down a group. What do you see? Are the atoms getting bigger or smaller? They're getting bigger. It's actually pretty clear as we go down. As you go across, it's not necessarily quite so clear, particularly because you've got this bit in the middle that doesn't seem to change much. But if you go sort of compare potassium to, say, bromine, these often are guesswork because they don't necessarily bond. So it's not so easy to work out what they are. But you can see that if you go across the group, what's happening to the atomic radius? Smaller. Well done, Caleb. Okay. So let's look at why. Now what I've done here is my own little images, which aren't that great. I just sort of threw it together. But I've tried to make the periodic table looking at the things relating to Coulomb's law. So don't worry about the K constant. This is the force of attraction. The Q1 is the nuclear charge, the charge on the nucleus. Okay, and Q2 is the charge on the electron. So the charge on the electron doesn't change because we're looking at the nucleus attracting each valence electron, and each electron is identical. So if we look at hydrogen, it's got a Q1 of +1 and a Q2 of -1. So there'll be that particular attraction that we can work out, and so that electron will stay in a particular area around that hydrogen. So I'm just using hydrogen as the base. If I go to helium, now Q1 is bigger. So what can you tell me about the traction between the nuclear charge and the valence electrons. Well, you've jumped a step, Caleb. Yep, it'll be stronger. So you've got a stronger attraction, and if something's attracting more strongly, it's going to suck it closer. So that's why you said smaller. So your electrons aren't going to be as far away. The shell actually decreases in size. So if you think of your electrons where they are, think of it in terms of two things. Distance, so the size of the shell where you'd find them, or the size of the orbital, as well as the energy. Because sometimes you can have a smaller shell with a higher energy, and sometimes you can have a larger shell with a higher energy. It depends on the particular orbitals. So in the first energy level or shell, they've got a particular energy, and these electrons have been sucked in closer, or they've been pulled in closer because of the stronger attraction of Q1. If we go to the next one down, right, oh yeah, sorry, I had a blank moment. I now have electrons not just in the first energy level, those are those blue ones. I've got 3 electrons, so the third electron goes into the second energy level. Now this is when you talk about the shielding, and Q1 now becomes the effective nuclear charge. So I was just thinking, I was wanting to ask questions, but this format is not so great for asking for long answers, so I won't ask you if any. Has anybody got know what effective nuclear charge is? And don't worry, I won't ask you to explain. I just want to sort of get an idea of you okay with it or not. Okay, no, not really. Okay, right. So basically, as I think I said in the booklet, if you've got a fridge magnet and you stick it on your fridge, it's got quite a strong attraction and it's not going to fall off your fridge. If you put a piece of paper on there as a note to yourself, it should also normally stick to the fridge. Okay, but if I put 3 or 4 pieces of paper between the fridge magnet and the fridge, what do you think is going to happen to those pieces of paper? They're going to keep on dropping off the fridge, won't they? Because that attraction is not as strong. The paper is doing 2 things. It's pushing the magnet further away from the metal in the fridge, so it's decreasing that attraction, and it's also forming a bit of a barrier. Okay, now it's not really much of a barrier for a magnetic field because it's just paper which has no field itself. But in an atom, you've got the nucleus, the valence electron in this second shell, but you've also got negative electrons in that first shell. So the 3 protons, that nuclear charge, is going to be attracting those electrons in the first shell, and then it's going to attract through that first shell to the second shell. So we say that those inner electrons shield, it's like the pieces of paper, but even more like, you know, more strongly, they shield the valence electron from the nucleus. So we can basically work it out that if I had a nuclear charge of +3, I've got 2 electrons in the inner shell, so that I can subtract 2 from my nuclear charge, so my effective nuclear charge is just 1. So can you see this has dropped all the way down to 1 instead of 3 as my effective nuclear charge? So it's not as strong as attraction. It's like the hydrogen one, you know, a 1 on 1, so we've got 1 on 1. The difference, though, is why lithium is bigger, is because the second shell is further away, and you know that the further away something is, the smaller the attraction. So if it's not attracted as strongly, it spreads out more. Okay, so it's, if you like, if you're trying to squeeze into something that's really tight, okay, it'll keep you in, but if it's something loose, you're going to spread out more. Yes, Correct, Rebecca. That's a good way of describing it. So what I've tried to show is, as you go across, my shielding stays the same in the group. So my shielding is 2 as I go across, because I've got 2 in the electrons. So my effective nuclear charge is going from 1, 4 subtract 2 is 2, 5 subtract 2 is 3. So it's only 2 less than the nuclear charge. So my effective nuclear charge is increasing as I go across, but not as much as it would have without those inner electrons. Okay, so as my nuclear charge is increasing, so if Q1 is increasing, what do you think is going to happen to F? Do you think F is going to get bigger if Q1 is increasing? Not sure? Okay, yeah. So if Q1 is increasing, then F gets bigger. So it means that attraction is stronger, and so it's going to pull the electrons closer. So that's why the atomic radius decreases across a group, and it increases down a group. It increases down the group because you've got more shells, okay, more energy levels. So the distance is further away, and you've got more shielding because you've got more inner electrons. So here the shielding was 2 in each case. Here the shielding is 10 each time. So it's this sodium had a nuclear charge of 11, but 10 of them are in those inner electrons. So it's again that electron is feeling just an effective nuclear charge of +1, the same as the lithium, the same as the hydrogen. Okay, so if you've got that sort of an idea in, then this is the way you would write it. Okay, so you talk about the protons. So if you think of pens, the more protons, the greater the nuclear charge. You've got to show you've understood that the nuclear charge depends on protons. So a lot of us, particularly the bright students, they want to be really concise, and they just sort of say keywords and they feel, well, that's it. But always think of your examiner or your teachers being really dumb, and you've got to spell out every little thing. Like if you say magnesium has got a bigger nuclear charge than sodium, then think of the teacher saying, why? I don't understand. Okay, so you've got to spell out that magnesium's got more protons than sodium, so magnesium will have a bigger nuclear charge than sodium. Okay, so the more protons, the greater the nuclear charge. Okay, and that'll mean that attractive force is going to be stronger on those valence electrons. We're always dealing with the valence electrons. And then as we're going across the period, remember we're adding it to the same shell or the same energy level. So the shielding, and notice I don't just say shielding, I explain what the shielding means. Because examiners want to see that you've understood the term. So the shielding from the 2 electrons in the first energy level. So you've explained, you've understood how it works. And then you talk about the distance decreases because of that stronger attraction. So do you understand why I've mentioned all those points? Because that's what you'd need for excellence. Okay. And so basically I'm saying is like if I've just got 3 protons, 6 protons, I'm going to have a stronger attraction, so it pulls it in a bit. 9 protons, it's got an even stronger attraction, so it pulls it in even more. Okay, and this is going across the period, so there's no extra shielding, no extra energy levels. If you go down a group, this is now when you're talking about the extra energy levels. So the more protons, the greater the nuclear charge. Okay, so you don't have to say that every single time. If you've said that under the period change, then you don't have to say it again under a group. You just simply say there's going to be increasing nuclear charge. But now you're adding the valence electrons to a different energy level, a higher one, or a bigger shell that's further away from the nucleus. Okay, so there's more shielding, and so there's going to be a small effective nuclear charge, so smaller attraction. And now you've got a bigger distance because you've got a bigger shell, so you're going to have a bigger atom. So what I'm trying to show here, as we just add energy levels, it's obviously going to get bigger. Okay, so that's just showing that it goes. Right, so the higher the first ionization energy, the smaller the atomic. Yes, if you're going across, if you're going across the period, as it gets smaller and smaller, you're going to have that stronger and stronger attraction, so it'll be harder and harder to remove an electron. So let's do that. Rebecca, I just want to do the ionic radius first, and then I'll get on to the ionization energy. So related to atomic radius, you've got to do ionic radius. So what I've just done here is, in red is the lithium ion. You can see it's smaller compared to the lithium atom. But anions, the anion is bigger than the atom. Now, page 33 in your books, there is a mistake. Please do not say this in an exam. So, it was said there that if you're looking at ion sizes, that the proton, the charge on the proton with attraction is shared over more or less electrons. There's no sharing. It's not as though this atom says, or the nucleus says, I've got 3 protons, so I'm going to share 1 proton to this one, and 1 proton to that one, and 1 proton to this one. There's no sharing. It's not like a basket of biscuits that you're sharing out amongst your class. Okay, it's just those 3 protons having an equal attraction to that one, to that one, and to that one. So what I'm going to try and show here is just a hypothetical element. You don't get anything with 3 protons and 3 electrons on the same energy level. I just wanted to get rid of the shielding and all that sort of thing. So my nuclear charge is +3 because I've got no shielding here. Okay, and I've got 3 protons. So if I look at this, I've got attraction, and remember, I've got repulsion. I've got repulsion between these electrons as they're going around the nucleus, as well as the attraction. So if I look at this, there's a certain distance away, and there's going to be a particular attraction. If I now, and then a particular repulsion as well. If I now change this and I remove an electron, so I'm forming a cation, then these negative charges can spread out more because they can move further away, because remember, they repel each other. So if I look at this, that's going to move further away from that one. But if I think of the amount of repulsion is going to stay the same because I haven't changed Q1 or Q2. So to keep that the same, can you see I've got to make it go smaller to keep that same repulsion? Okay, and so the cation is smaller. Now we'll see another reason why when we look at real atoms, and it's the loss of the outer, an energy level, but it's this idea of the attraction is balanced by the repulsion. So if I've got less repulsion, then the electrons can move closer to the nucleus. And so you can see, to keep that the same, because it stays more or less the same. It'll be slightly stronger, of course, because remember, we've changed the distance. Okay, if I look at this one and I add an electron, now we've got what? More repulsion or less repulsion? I've added an extra electron, more. But the repulsion will still be the same. Okay, it's just they've got to now try and keep the actual force of repulsion the same. Sorry, it didn't sound very good. If I add the electrons, just overall I'll have more repulsion, but the repulsion between each 2 electrons will be the same. So they're going to spread out more to keep that attraction the same, or repulsion, sorry, the same. and that's would make it bigger. So if I then look, so over here, here's a proper example of magnesium. Magnesium has atomic number of 12, 10 inner electrons in the core, so it's got an effective nuclear charge of 2. And so if I now take the outermost electrons off, can you see my inner electrons? This second energy level now becomes the valence shell, and this is now the inner electrons. So my shielding has changed from 10 to 2. So can you see how much bigger my effective nuclear charge is? It's a lot more. And also notice that if I go, the distance is now smaller for 2 reasons. Because can you see it was in the third energy level that we had to attract? Now it's in the second energy level. So it's already come closer just by the loss of a energy level. And by having a higher effective nuclear charge, it's going to attract them even more strongly. And that's why cation is quite a bit smaller than the atom. Is that clear? Does that make sense? I know I'm doing a lot of talking, so you're welcome to interrupt and ask questions. Okay, formation of anions is pretty much okay. Here we keep to the same effective nuclear charge because we are not, can you see I've added an extra electron there? We have not changed the nucleus at all. Yes, Rebecca, so it's like that. And think of the paper as being magnetic itself, so it interferes. So if you had a south pole attracting a north pole, and you put the paper on the south side, you know, yeah. So here, what would happen? It would go to keep it. Oh, sorry, go back. It's got to spread out more to keep the same amount of repulsion, and that's why it takes up more space. So the effective nuclear charge is still the same, but because of now the repulsion force, it's got to spread out more to keep that the same. So they've got to take up a bigger distance to keep it the same. Okay, so I know we're pretty much, because I said half an hour, so very quickly, ionic radius. Actually, what would you like me to do? Would you like me to continue with this next week, or would you like me to just quickly go through this now? Because I did say half an hour. Now it's good. Okay, so we've just got ionic radius and electronegativity. So, ionization energy and electronegativity. But this is how you would answer an ionic radius, a 1. So, Rebecca, this is the way you would answer it. Pretty much whatever way they ask it, this is sort of what you answer. If they give you specific examples, then you would talk about the specific thing. So if I was talking about magnesium and sodium, or why is the sodium atom bigger than the sodium ion, for instance, then you would talk about that. Okay, so here you've got the atomic size decreasing, but the ionic size across the period decreases because we're getting a bigger and bigger charge on the cation, so it's a stronger and stronger attraction. And if we go to then the anions are part of the period, then the greater the charge, so N3 minus, has got now 3 more electrons, so a lot more repulsion. So those electrons have to spread out more to keep the repulsion more or less the same as they had before. But you'd keep it an answer like this. You just adapt it slightly to any specific examples. So anions are bigger because of this repulsion between the negatively charged electrons. Cations, whoops, I've gone. Cations, you would talk about getting smaller because of the loss of the energy level and the stronger attraction because your effective nuclear charge is now a lot bigger. Okay, so this is going down the group. So something along those lines. Okay, now ionization energy. This is, now there's two things you must remember here. It's atoms in the gaseous state. So it's not like chlorine gas, Cl2. It's the atoms. Or it's not sodium metal in the solid state. You've got to pretty much heat it up until it becomes atomic. It's nearly like a plasma rather than a, although it's got to be in a gas state. So you heat it up, and this is the way you work it out, or you measure it. So it has to be in the gas state. Now at level 3, you have to include states in all your equations. So you can't just say Cl going to Cl plus electron. You have to say Cl gas going to Cl plus gas plus electron. Okay, electrons, you don't have to say that in the gas phase because it's not really a species in itself. Okay, so what is the first ionization energy? Is to remove the one electron from the outermost energy level. So we're removing one valence electron, and it's the one that's least tightly held, and that's, as I said, will always be in the outermost valence energy level. So it's also for 1 mole of atoms. So it's not just one electron, it's a mole of them. And you'll notice that our units are kilojoules per mole. So how much energy is needed to remove 1 mole of electrons from 1 mole of chlorine atoms, gaseous atoms, or something like that. Right, so if I'm removing an electron, it takes a certain amount of energy to do that. So how can we explain the changes in energy? Why is it increasing? So if I go across a period, it gets harder and harder and harder to remove an electron. Now a lot of students go on about stability. They'll say helium has got an octet, so it's the most stable, so you can't remove an electron from it. That's like level 1 thinking. Level 3 thinking, you have to talk about pens, number of protons, nuclear charge, effective nuclear charge, and so on, number of electrons. So you'll notice that the explanations are very similar. Doesn't matter if you're talking about electronegativity, ionization energy, or atomic radius. So here it's the same thing. As you go across a period, you have more protons in each element as you go across. So you can have a bigger nuclear charge, so you can have a stronger attraction between the nucleus and the valence electrons. Because of its stronger attraction, it's going to be harder to remove a valence electron because it's held more tightly. And now you talk about the electrons are added to the same energy level, so you've got the same shielding, and the distance effectively remains the same. I mean, it decreases slightly, but not very much. It's not like going down the group where there's a big jump to another energy level. So the distance, decreases, but not as much, but it is enough to make it harder to remove an electron. So although I said it's not much of a change, because you saw that it just slowly got smaller and smaller, but it is enough to make that attraction stronger, so it's harder to remove an electron. But it's probably really because of the effective nuclear charge or the nuclear charge getting bigger all along. They support each other, but I'd say this is the more important one than that. But please mention both in the exam. Any questions on across a period for ionization energy? Because I know I'm going quite fast. No. Okay, so pretty much what I'm trying to show here is that I don't need much energy to take this one away, because this one's only got an effective nuclear charge of 1. Okay, nuclear charge of 3, effective nuclear charge of 1. Here I've got a nuclear charge of 6, but an effective nuclear charge of 4. So it's a bit harder to take my electron away. And here I've got 9 protons, effective nuclear charge of 7, and so it's going to be a lot stronger pull, attraction between the nucleus and the valence electron, so it's going to be a lot harder to take the electron away. Okay, and then, great, I'm glad that helps. And then, as I say, this distance, I'm trying to show that the distance gets smaller. So the brown is the attraction between them, so the attraction is getting stronger. But I hope you can see that this is slightly smaller than that. So it contributes to it being harder to remove that valence electron because it's a smaller distance. But you can see it's not such a big thing that like the nuclear charge. Now down a group, we're getting into an extra energy level. So if you think of here, this is hydrogen, and I go to the next one down, lithium. So the effective nuclear charge here is 1. It's 1 as well, because it's 3 subtract 2 is 1. Here the effective nuclear charge is 11 subtract 10 is 1. So the effective nuclear charge is sort of staying the same. Okay. Doing that straight subtraction is a slightly simplistic thing, but it tells you, it gives you an idea. So we're not changing very much the effective nuclear charge. So the nuclear charge is increasing, the effective nuclear charge is not changing much because of more and more shielding. But notice that the distance is getting bigger and bigger and bigger. Because the distance is increasing a lot, you're going to have a weaker and weaker attraction between the nucleus and the valence electron, so it's easier to remove something, say, from potassium than from hydrogen. Does that make sense? Yep. So electronegativity, this is the last type of thing you need to know, and this is where you're looking now, you're not talking about valence electrons anymore, you're going to be talking about bonding electrons. Because the way we talk about electronegativity, it's a property of a bonded atom, so it depends on the element, okay, not the molecule. So although it's bonded, it's still the property of the element, the atom, not the whole molecule. I can't say the electronegativity of water, because it doesn't have a thing like that. I can talk about the electronegativity of oxygen in the water or the electronegativity of hydrogen in the water, but water doesn't have an electronegativity. So if this was, say, HF, then hydrogen shares its electron with fluorine, and so what would happen is fluorine has got because it's on the top right, very much stronger electronegativity, so it actually draws those electrons more strongly to itself and leaving hydrogen pretty much bare. So it's that attraction to those bonding electrons. So I'm trying to show it's stronger to there than stronger than to that nucleus over there. Now, as I said here, just write about bonding electrons, not valence electrons, when you're talking about electronegativity. And I've already mentioned that. Okay. So can you see what I've got up there? It's nearly identical writing. So you could actually rote learn this if you want to, just so be prepared to understand it enough, so if they give you a specific example, that you phrase your answer to that specific example. So it's the same thing. As we go across the period, we're adding more protons to the elements. Means I've got a bigger nuclear charge, which means I've got a stronger attraction between the nucleus and the bonding electrons. Okay, but because we're going across the period, we're not adding it to more energy levels. It's the same energy level, so the shielding stays the same. So our effective nuclear charge is definitely increasing because we have the same amount of shielding, and that would make that attraction stronger. So it'll have a, therefore there'll be a bigger electronegativity. It'll attract those electrons more strongly. And because the size of the atom decreases as we go across the period. We're going to have a slightly smaller distance from left to right. It's going to be smaller on the right. So again, if D decreases, we're going to have a stronger F. It'll be a stronger electronegativity. Okay, but as I said, when you go across the period, the nuclear charge is more important than the distance, although they both have an effect. So here what I'm trying to show, the same thing as we had with ionization energy, except here we have bonding, you know, they obviously bonded to something else. Down the group, same thing, except we talk about bonding electrons. So it's exactly what we had before. So potassium has got a lower electronegativity. If it was bonded to something else, it can't attract those bonding electrons as strongly because they're just so far away and they're shielded by all those inner electrons. Okay, and I think that is about it. So, okay, what I've just got here is Lewis structures, which I want to do in the next lesson. Pretty much if we use electronegativity in Lewis structures and to work out whether a substance is polar or not polar. And that'll be from 304.2, and we'll do that next lesson.